Okay, here's the second problem. This one here has a shaft with two pulleys on it, and in this case, the two pulleys are going to put both a torque and a bending moment on that shaft. So imagine that this shaft can spin, all right? So there's two bearings on either end of it. They can just freely spin in those supports. So the supports aren't giving us any kind of a torque load, but there is a torque from those loads that are hanging from the bearing from the pulleys, and as you might guess, also, those loads are trying to bend that shaft as well. So what we're going to do is try to find the principal stresses and the maximum shearing stress at this point A, right here at the top surface of the shaft. Now notice that the steel shaft has a diameter of 4 inches. The pulleys themselves are 2 feet in diameter, and they're keyed to the shaft. Keyed to the shaft just means that they're they're rigidly connected to the shaft. So they're not just gonna spin on the shaft. They're gonna turn with it, and that's important when we're talking about what kind of torque they put on the shaft. And then the shaft, like I said, we've got flexible bearings at each end, so they're just gonna allow the shaft to spin. So let's look at just a couple of things before we write a free body diagram here. These loads right here, the 2,500 and the 400 pounds, because we have a 2-foot diameter shaft, right? So this means that the radius here is 1 foot, right? Let's let's make it clear then that we've got a torque here of 2,100 foot-pounds, and that's because of those two loads that are right there. On the other pulley, we've got a torque of 2,100 foot-pounds in the other direction. All right. In addition to those torques, you can also think of these loads right here as being kind of a point load on the shaft. So I'll just make these longer like this. This is going to be like 2,900 pounds at those two locations on the shaft, like point loads. All right. So we're going to have these two torques that are going to try to twist the shaft, but we're also going to have these 2,900 pound point loads that are going to try to bend the shaft. So those are our two loads. Those are the combined loading cases that we're talking about, and together they will give us some sort of a stress at A that we're trying to figure out. So let's also add, into the things that we've already calculated there. Let's also make a few side calculations here. We're going to need a polar moment of inertia for that shaft, because we're going to have a torque on there, so we're going to have to calculate a shearing stress. And because we've got a 4-inch diameter shaft, we'll make the calculation like this. That'll give us 25.133 inches to the fourth. We're also going to be bending this shaft, and so our second moment of area for that is going to come from pi over 64 d to the fourth. All right, and this here is going to look like that, right? As if we were bending about this x-axis, right? Because that's what we're going to do. We're going to be bending about that axis. So pi over 64 d to the fourth, 4 inches to the fourth, is going to give us 12.566 inches to the fourth. All right, so that's some preliminary details. Now let's draw a free body diagram to consider what kind of bending behavior we're going to have, what kind of bending stress, flexural stress. So free body diagram for that will look like this. We'll have two pulleys here. Haven't quite figured out why it does that from time to time, that little mark. So we've got 2,900 pounds coming down from each pulley. And that means the reactions at the two ends are going to be pretty easy to figure out. They're just going to be 2,900 pounds as well. If we put together a shear diagram, so this will be shear in pounds, then we're going to have a diagram that looks like this, like so. If we put together a moment diagram, this would be in foot-pounds. Whoops. If we put together a moment diagram, that's going to look like this, where this level right here is going to have a moment of basically the integral under this part of the shear curve, which is just going to be 2,900 times 2 feet. That's from our diagram on the previous page. So that's going to look like 5,800 foot-pounds right there. So basically the moment that we have at A is 5,800 foot-pounds. So let's do a calculation of our flexural stress at A. So that's going to look like minus M, and I'll just say, I'll just keep calling it M like we have on this chart down here. It's going to be minus M times Y over I, and in this case our Y is going to be the radius of the shaft, and we calculated our I already. Let's convert that 5,800 foot-pounds into 69.6 inch kip, because our Y and our I are both going to be in inches. So we'll do that. We'll have minus 69.6 inch kip. Our Y, because it's on the top portion of the shaft, it's going to be 2 inches, positive 2 inches. And then our I, like I said, we already calculated that, 12.566 inches to the fourth. That's going to give us negative 11.08 KSI. All right, so basically that tells us that the top surface is in compression. Let's make it a little clearer that that's a 0.08, 11.08. All right, so that gives us flexural stress at A, but we're also going to have some shear stress at A, because this thing is in torsion. All right, so let's go to the next page here, and we'll make a free body diagram of this thing for the torque, because we need to find the torque at A. And if we do that, we'll have a shaft that looks like this. This is point A. We already know that we've got a torque of 2,100 foot-pounds from that pulley. And then if we make a slice anywhere in between the two pulleys, we've got this torque at A, like this. If I do a sum of my moments, I'm going to have 2100 foot-pounds, and I'm going to have that TA equals 0. So my TA is going to be minus 2100 foot-pounds. And if I draw that just the same way that we can draw a shear and bending moment diagram, I can draw a torque diagram that will go across the whole thing. The torque from the end until I get to that first pulley is going to be 0. Then I'm going to get something that looks like this up to the other support. So this torque right here in between the pulleys is negative 2100 foot-pounds, which I can also write as 25.2 inch kip. All right, so then that means that I can do my calculation of the shear stress like so. So the shear stress is going to be tau xy equals the torque times C divided by J. We've already calculated all these things. I've got a negative 25.2 inch kip. I've got a 2-inch radius on this shaft. Whoops. 2-inch radius on this shaft. And the J we already calculated to be 25.133 inches to the fourth. So that gives us negative 2.01. Ugh. All right. So now I've got both my my shear stress and my sigma x. So I could say in this case I've got the following stress element to find our principal stresses. So let's go back just a moment here and find what we had for the flexural stress at A. It was negative 11.08. So that's going to be a we could say that our flexural stress at A is compressive. So we've got, and it doesn't necessarily matter what we call x, but let's call that x, negative 11.08. I'm sorry, I don't understand why I keep. There's nothing I'm pressing. There must be some hidden piece of this screen that's like automatically go to the end of the document, and I don't know how I'm pressing that button. So I'm sorry, everybody. And then I'm also going to have a negative tau xy. That's going to give me something that looks like this. So my tau xy is negative 2.01 ksi. If I do my calculations of all my principal stresses, which I'm not going to put into this example problem, I'm going to get 0.353 KSI. Man, that little spurious little jump like that is really annoying. 0.353 KSI, negative 11.43 KSI. And of course, since we're on the surface, my sigma P3 is 0, which then if I calculate tau max as sigma p max minus sigma p min over 2, then that's going to give me 5.89 KSI. And that's it. So another combined loading problem where we have bending and torsion in the same shaft, and we can work the rest of our problem just like we do just like we have done with our previous problems in principal stresses. So let me know if you have any questions on that.